this problem from sequence of function and uniform convergence, right? And the problem is fnx, this is equal to e to the power minus nx, where x belongs to d and d is given by d, this is equal to 0 to infinity. This is the given region. So that the sequence fn converge to a function f on d. Okay, this is the first problem of this class. Now we solve one by one. Now we first solve the first question. Here fnx is given by e to the power minus nx, right? Now if x this is equal to 0, because here d this is equal to 0 to infinity, so d this is equal to x such that 0 less equal to x less than infinity. This is the set. If x equal to 0, then we get fnx, this is equal to e to the power minus 0, this is equal to 1, and this is f of x, that is the limit function of the sequence of function fx at x equal to 0. Now clearly if 0 less x less infinity, that is x not equal to 0 but belongs to d, then we get the limit function as limit n tends to infinity, that is limit n tends to infinity e to the power, this is fnx we write here, and this is e to the power minus nx, and this is e to the power minus infinity, because n tends to infinity and x not equal to 0. So this is given by e to the power minus infinity, so this is 0. For or at, this is we write for 0 less x less infinity. Okay, so we say that the answer of the first problem is f of x, this is the limit function, we know limit function of the sequence of function fnx, this is given by 0 if x equal to, this is given by 1, this is given by 1 if x equal to 0, and 0 if 0 less x less infinity. This is the limit function. And now we go to the second problem, the problem number 2. It is given that so that f is not continuous on d. Okay, we already get the function fx, and clearly f of 0 this is equal to 1, but limit x tends to 0, f of x this is equal to 0, because here the domain d is 0 to infinity. So for check the continuity at x equal to 0, we have to find the functional value, that is f of 0, and the right hand limit, because there is no left side of 0. So we get limit x tends to 0 plus, and this is the same as limit x tends to 0 fx. Okay, so this is 0. That is, we say that this is not equal to the functional value. Hence f of x is not continuous at x equal to 0. Okay, so this is the first part of the second problem. Now we go to the second part of the second problem. Deduce that the convergence of the sequence fn is not uniform on D. Okay, So for this problem we have to use the first part because it is given that deduce from the first part. Okay, and we use a theorem of sequence of function related with continuity, and which gives if fnx is continuous on D, okay, that is the domain of definition of fnx, and if fnx is uniformly convergent in D, then f of x, that is the limit function must be continuous. Okay, we use this theorem, we write the statement of this theorem. Here fnx, this is equal to e to the power minus nx for all x belongs to D. Here D, this is equal to 0 to infinity. Okay, and we know that the exponential function, that is the e to the power minus x, is continuous everywhere, right? So we say that fnx is continuous on D. Okay, but here we already see from this relation, that is the limit function is not continuous in D. Okay, but fx is not continuous at x, this is equal to 0, and this point belongs to D. So our theorem is not satisfied, because if fnx is uniformly convergent in D, then fx, that is the limit function, must be continuous. Okay, so we say that, so we can say that fnx is not uniformly convergent on D. Okay, and this is the solution of the second part of the second problem. Now we go to the third part of the problem. So that the convergence of the sequence fn is uniform on a to infinity if a greater than 0. That is, if we excluded the point A, okay, we excluded the point A by any other point greater than 0, okay, then the sequence of function which is not continuous at D, but this is this is uniformly convergent on A comma infinity, where A greater than 0. How can we see this problem, or how can we solve this type of problem? Here we first write fnx, this is equal to e to the power minus nx for x belongs a to infinity, where a greater than 0, right? And in this case, if we find out the limit function of this problem, then we cannot get this part, because there is no 0, that is no value of x which is 0. So we get only 0 functional value, or only the value 0 of f of x in this interval. Okay, so in this case fx, this is equal to 0 for x belongs to a to infinity, or we can write this. Okay, now we assume a pre-assigned epsilon greater than 0. Okay, we assume pre-assigned epsilon greater than 0, and we let fn x minus fx less than epsilon, and we put the value of fn x, which is given by e to the power minus nx, and minus f of x, this is given by 0 less than epsilon, and this can be written as e to the power minus nx less than epsilon, because e to the power minus nx is positive for any value of x, right? And get e to the power nx greater than 1 by epsilon, and taking logarithm on both sides, we get nx greater than log 1 by epsilon. Okay, now from this relation we get n greater than log of 1 by epsilon by x. Now we see that x is lies between a to infinity. Okay, and if we put here a in place of x, then we get the maximum value of n, because if we put a, this is smaller than x, then this value is the maximum value of n, and in this case we can choose k. This is equal to box of log 1 by epsilon by a plus 1. Okay, and we write the definition of uniform convergence as mod of fnx minus fx less than epsilon for all n greater or equal to k. Okay, that is epsilon, sorry, that is k is depend only on epsilon, but not on the value of x, because from this relation we see that k is depend on epsilon but not on x. So we can add another point here for all n greater or equal to k and for all x belongs to b, and this is the definition of uniform convergence of fn, right? And so we say that the sequence of function fn is uniformly convergent if we take a comma infinity in place of 0 comma infinity, where a greater than 0. Okay, so this completes the total answer.